All right, we're going to use the audio on my laptop. That probably means I should up the microphone audio as well. All right. I guess so. We have audio on Zoom now, on Twitch. Let's roll. Okay, perfect. So we don't need that. We'll do video. There we go. From my laptop as well. It's not going to be fancy wide angle, but it'll be functional and not choppy. All right. Sorry about that. Let's roll. So this is, of course, the next week of 466/pwn.college, week 8. We're going to start, as always, with a meme review, state of the class, and then we'll go on from there. Let's increase the volume on the mic there. Okay, perfect. So, where are we so far meme-wise? We got a couple of good meme categories this time around. One of them is this great meme heralding a return to in-person classes. My daughter also goes back to daycare, so probably I'll be sick this time next week. But hopefully it's supposed to take a little longer between daycare visits to get sick. I want to apologize to everybody who may have been impacted by my opening of a Java GitHub repository on live stream. I'm sorry you had to see that. Java shouldn't be seen by anybody, or no one should be forced to view Java. It's just not right. I'm sorry. But we'll try to avoid it going forward. This is I just like this meme for aesthetic reasons. You know, it's like just aesthetically funny, like the way it, you know, it's pretty good. It's a good artistic one of these artsy memes. All right, another category of meme, kind of more high-level, abstract pwn.college memes. So one of them is Toddler 1 is coming. Be ready. We're going to make Toddler 1 a little more approachable than it has been in the past, but no easier. Right? But it's going to be a pretty exciting test of all of the things you've learned so far put together. And that'll be great. We think you're gonna love it. All right, we've got another category. This is all about overflows, and this is great. I love that one up there. I don't really know what it's referencing, but in my experience, like the closest in my video game experience, I'd say is like a Zerg Rush. It would be also a good meme for that. That's a great buffer overflow meme. Connor, have you been changing the binaries in BabyMem silently?
Yeah, a little bit.
So Connor's been fixing some bugs, silently changing binaries in BabyMem. Sorry if this impacted you. In the future, hopefully we'll remember to announce changes to
Everything important was announced.
Everything important was announced, but keep an eye on the announcements so that you don't find BabyMem suddenly swapping out on you. Exactly. Connor broke all your scripts. Let's catch up on Twitch. Awesome. All right. So, yeah, this one's great too. Good memes. Now, hopefully everyone's made it to the later levels. I mean, I know not everyone's made it to later levels, but things get pretty fun after a while, right? You can start leaking things creatively, brute forcing things creatively. It's it's good stuff. And this is all knowledge that you'll put to use in the rest of the class, of course. All right. Another category. This is a little bit of a grab bag because I threw this one in here. This is pretty funny. But there's got to be like a video of Baby Jan actually doing that. There probably is. And the rest of these are all, memes around the concept of corrupting stack canaries. For the most part, I am a big fan of this meme. This one's weird. Stack smashing detected is the new wrong no flag for you. Who likes no flag for you better than stack smashing detected? So who likes stack smashing detected better than no flag for you? All right. Who likes them equally? All right, so that should have had everybody one of the three options. But all right, we'll work on class participation a little more. Someone said on Twitch, it all hurts. Good times. All right, so update on the state of the scoreboard. So of course, this was the state of the scoreboard before we launched Baby Mmap. This is the state of the scoreboard after we launched, half a week after. So we already have quite a few people that got the 30 points of Baby Mmap. Top 20 has been filled. And once again, top number 1 is a worldwide student. So great job, Dirac Delta. And then great job, PyPy. And Bis, Trees, and JT Parida. Let's keep hacking. There's plenty of other spots on the scoreboard still available. Actually, let you in on a little secret. There is no functional limit. Maybe int max is the limit to how many spots on the scoreboard there are. So, you can always get on the scoreboard somehow. But my screen is only big enough to show 20 spots. All right, let's talk about Ctf Extra Credit. Don't forget, there's plenty of extra credit opportunities. There's meme extra credit, helpfulness extra credit, Ctf extra credit, and bug bounty extra credit. Is that all of them? I think so. Ctf extra credit, we had 8 students from the class, 8 ASU students participating in CTFs last weekend on 3 teams, including one on Shellfish. They played 2 CTFs, so most everyone played TGS, and Shellfish played Tasteless. And Shellfish got 10th place in Tasteless. Great job. TGS was a super tough CTF. The total solves other than the sanity check was 1. It was a great solve. Good job. Awesome. All right. What else on there? Just remember, play with a team, or reach out to Shellfish or another CTF team if you know them, and you can get 1 percentage point per weekend. Next weekend, there's Perfect Blue Ctf is coming up. It's going to be an awesome CTF. Perfect Blue is an awesome team that were competing at DEF CON this year. So the CTF should be wild. A lot of teams registered for that. Possibly more introductory CTF is this SPB CTF, student CTF. I don't know anything about this, but the fact that it's a student CTF makes me think that it should be more introductory. And that might be another thing to explore. So one of these two, or any of these are valid. Go tackle them and play. All right, we have a question on Twitch if anyone's gotten a bug bounty. I don't think anyone's gotten a bug bounty this semester, no. Did anyone get a bug bounty last semester?
I think only the first semester.
Yeah, I think we've only given out a bug bounty the very first semester we ran pwn.college. That was a pretty serious one. But since
There
then,
was an available one this year, but no one caught it.
yeah, Connor got a bug bounty this year. All right, cool. So, helpfulness extra credit. We have a new development. So Charco is relentlessly pushing up the scoreboard. If they manage to unseat PyPy, who's also fighting hard to stay ahead, it's gonna be quite an epic battle. As we discussed, Charco agreed to, since Charco's not an ASU student, they agreed to donate their extra credit evenly distributed to the rest of the class. So that would be great. But otherwise, Charco is coming. All right, awesome. Let's, is there a way, so there's a question on Twitch, is there a way to see how much extra credit you have with helpfulness? Do we have a way to see the extra credits yet?
No, that's soon.
Yeah, definitely not with helpfulness because we need to match Twitch Discord handles to your pwn.college IDs, so that'll come soon. And with write-outs, you just need to expose that information. I'm sorry?
I don't know. I was saying I would lie about who I was to get more points.
Yeah. Are you PyPy or is this person PyPy? I see.
No, he's PyPy.
Good. All right. Yeah, you can pretend to be PyPy. All right. Awesome. Yeah. So you'll need to, of course, figure out how to properly authenticate Discord. Anyways, this it's never easy, but okay. Where are we in the class? We are on the memory corruption second day. So on Thursday, I talked about how to use GDB and dynamic techniques to understand sizes of buffers and stuff. From what we've been seeing, everyone embraced that wholeheartedly, and now we're thinking, man, how do we actually make them use IDA to understand the size of buffers? But maybe you have had to do that in the later challenges already. This is the last class of memory corruption. On Thursday, we're moving on. We're moving on because it's going okay, right? Even 2 days before the deadline, we have a bit of a chaotic spread, but of course this is just 2 days before the deadline. But there's definitely some people that are doing better on Baby Mam than did on Baby Rev. We have a spread of scores, of course, too many E's, but they are mostly from a lot of people that haven't started yet, which is always disheartening to see this close to the deadline, but that is what it is. But the spread looks a lot better. If you remember, after the first weekend of Baby Rev, the spread was still quite bad. But things look a little better. People are starting to get more and more challenges. Hopefully, people will really kick it into gear because otherwise it's going to be tough. But we're moving on Thursday to Toddler 1, and Toddler 1 is built in to go past fall break and another entire week. It's going to be 2 weeks of awesome challenges. All right. And of course, if you're done with the Toddler 1 challenges, but you missed some earlier challenges, you can go back and make up that difference retroactively. All right, so the summary, all of the deadlines, Baby Mam due on Thursday. Everything else is still doable for partial credit until December 12th. Any questions? All right. No questions. Level 2 is a question. All right, so we can start going through some concepts. Otherwise, feel free to interrupt if you have questions. All right, let's tackle some concepts. All right, so let's spin up level 2. and go from there. So I'm going to try to show conceptually approaches to problems. They're not always, that's not always easy to do without walking through the entire problem, but we're going to try not to just walk through the entire problem. And I think I still have the insane, whoa, that was a stupid thing to do. Let me, tab completion failed me. All right, that's gonna have to get burned. That was epic. Luckily, I think it was my desktop key that was on here right now. All right, well, that was the dumbest thing I think I've ever done while streaming, but that was great. That was great. Oh, that was the best. All right, anyways. Let's dive in and see what that is. Amazing. All right. All right, baby mem level 2. Let's take a look at how to approach it statically and then how to approach it dynamically. Actually, dynamically first because it's just easy to run it and see what it says. All right. So the we have a win variable in this level, and when the win variable is non-zero, the flag will be printed, and the win variable is stored 512 bytes after the start of my buffer. And Connor, why does this talk about a win function? So let's take a look at the binary statically now.
There's always a win function, so it's just reporting its existence.
Yeah, we should fix that. All right. Anyways, Connor will fix that and probably regenerate binaries again. But let's is that the ventilation taking off? Wow. All right, let's pull it down. What? Okay, there we go. All right. So let's run IDA, see what it's like. All right. So we call the challenge function from main, go in, this prints a bunch of stuff. All right. And then, so it asks us what our payload size is going to be, and we saw that when I ran it dynamically. Let's actually SSH back in. If I do payload size 10, then it says, okay, it tells us where we're gonna, our input is going to start being written in memory, where it's going to be written to, how many bytes beyond the end of the buffer that was, so I didn't quite actually make it past the buffer with this payload size of 10. Connor, this should be a signed integer. Yeah. So let's say I do this and I say, okay, I want to give it 1525 bytes. Oh no, Connor, this is just broken. All right, that's confusing. I'm sorry. We're fixing that. So it's 5 bytes beyond the end of the buffer and some amount of bytes into our return address. Obviously, this is just broken, but we'll fix it. And in this case, Connor, I think we might have a
No, the issue is that it's just reporting stuff about the level that it doesn't need to report.
yeah, exactly. That's a big issue. Okay. So this level is trying to be a little too helpful and giving. This seems like a bug in our template to generate the level. But let's say we send our payload.
Can you also zoom in?
Yeah. Send it a bunch of A's. All right. So memory status of the program. The input buffer starts somewhere. The address of the win variable that we need to overwrite is somewhere else. The value of the win variable is still 0. And there is a win function whose address is being reported anyways. All right. No, Connor, this all right, let's switch from the yeah, we're gonna go to the testing version of this challenge. Sorry about that. That was definitely unintended. Do you think all of the trainings are broken?
Just the first two that doesn't matter what the win function is.
Okay.
It's just reporting information about the win function. And
I see. Yeah. So just superfluous information that we didn't catch. All right. So let's copy in the new challenges. So, okay, let's do Baby Mem 2.1. Payload size, payload, boom, goodbye. Much nicer, no crazy superfluous stuff. All right. Let's open this up in IDA. All right. And here we can see this being much simpler, right? No more printfs, no more etc. We read in the payload size, then the program reads in this many bytes, and then if we overwrite another variable on the stack, we win. Nice and easy, right? Or sorry, not on the stack. V6 is allocated from the function calloc. V7 is allocated from Malik. Let's just take a look in GDB and see where all of these addresses are, or what everything points to. So let's name this. I see. This is our buffer. Then there's some other stuff that's allocated, and then this guy is allocated, and this is our win variable. Let's go back here. Enable addresses. Awesome. All right, where's that win variable? Okay, here's where we compare the win variable. Where's our buffer? Here's where we read into the buffer. So we're going to break at read. We're going to see where that address is. And then we're going to see where the address of the win variable is and then we will understand how much to overflow to get it perfect. All right. So, gonna run baby mem and GDB. Break, rather than at the read libc function, let's just break at this calling code. And if you recall, I have an automatic base variable which just says where GDB will try to load this binary. Since it's position dependent, can break at base plus blah. Okay, that's where the read will happen, and then from the read we're just gonna step until we get to this this read of the win variable. Then we'll figure out where it is, because it's going to read the pointer to the win variable into RAX. All right, so we run this payload size. Let's just put 10. Okay, now we're reading. Do next instruction, give it a bunch of A's. I guess we need to give it exactly 10. Okay, boom. Now we'll just go next. Okay, here we are at 1FF0 into the binary, and this is exactly where we read that win variable. All right, and oh, I forgot to print out. Fuck. Okay, so let's just get where the win variable is located. Win variable is located at this address, 5555A8C0. That's a little strange, actually. Is that really on the heap? What the fuck? I'm having a massive brain fart right now. Sorry. Yeah. What? Okay. Maps. Map. Okay. Whew. Okay. That is the heap. Okay. Awesome. All right. So we printed out this variable, which is the, let me also zoom in here a little bit, which is this win variable, the address of it, that is dereferenced to figure out if we get the flag or not. Now, and we saw something weird. We saw that instead of being on the stack or anything like that, it's in a weird memory region that we looked at and saw this memory region named the heap. Why is it there? Baby heap is not for another a couple of weeks. It's there just because it was allocated using Malik. All right. So, as I mentioned, you should have a comfortable grasp of C for this class. Who here has used Malik in the past? All right. Go check out what Malik is. Malik is a way to allocate dynamic memory. Right? You call Malik in a C program, gives you a pointer where you can write however many bytes you allocated. Now, of course, similar to a local function stack frame, that buffer can be overflowed. And that's what's happening here. Malloc and calloc and realloc They're all style or little different ways of invoking the allocator. If you look at what calloc is, why do we care? Because the win variable is allocated with calloc. Calloc will allocate memory for an array of n member elements of size bytes each. So that is n member size bytes each. Here we allocated one element 4 bytes each. And the memory is set to 0. So why did we use calloc here? So that it is set to 0. So basically you have two allocated memory regions. We need to understand what the width is between them, and we can do that in GDB. We cannot easily do it in IDA because the behavior of Malik is tricky. You'll learn all about it and become intimately familiar with it in Baby Heap. But for now, we can see where our buffer is allocated versus, or you know, where our buffer that we're reading starts versus where the win variable is located, and figure out how much we need to overwrite. Okay, so let's do this again. We'll break at wherever we call read, which is this address. Okay, we'll run it. We'll give it a payload size of I don't know. Let's do 1. All right. That's the file descriptor we're reading from. Second argument is the buffer. So the buffer is located here. You continue input A. Oops, instead of continuing. 1. Okay. This should be the same. Yep. Here's the buffer. Next instruction, input A. And then let's keep walking. There we go. Okay, now we read the address of the win variable into RAX. Here's the address of the win variable. Let's see what payload size we need by taking the address of the win variable, subtracting the address of the buffer. The win variable is hex 210 bytes after our buffer. So if we write 211 bytes, we're good to go, right? So we can do that. Oops. What is hex 211? We don't need to know that. We'll have Python help us. Boom. All right, so I guess that was the full solution there. All right, so what did I do? I looked in IDA for what this program is doing. I traced it in GDB to figure out with the size of the write that I need to actually reach that win variable that I need to overwrite, and then I did it. The fact that this memory was allocated using Malik versus being allocated onto the stack turned out to be quite irrelevant, and it often is. Of course, in trickier situations where memory is allocated is extremely critical, but in this case, all we really cared about is that distance between the buffer and the win variable. Cool? All right. So there are Malik is one way of allocating memory. And I guess we might as well take a quick look, since not everyone has experience with it, and talk about Malik and talk about Mmap, right? So you remember, hopefully, different sources of memory, different types of memory. We have the stack, which you're probably fairly familiar with. We have the heap. We have memory that is loaded in as part of the ELF file, global variables, stuff like that. And we have kind of arbitrarily mapped memory beyond that. So let me show you what this means. Let's write a program.c, and program.c is going to read, it's going to print us its own memory mapping, right? Now you saw me type info proc maps in GDB. You can do the same thing in the program programmatically by looking in the /proc file system in Linux. It's a very useful file system with a lot of information about processes. So let's, let's have a buffer. I don't know, it should be pretty big. We're gonna open /proc self maps. If you look in the proc file system, there's a lot of information about processes. There's some cool stuff in here. So you can actually look up all TCP connections that your system currently has open. For example, they're all exposed through this. It's a virtual file system. These aren't actual files on your hard drive. And this is how netstat works. You do netstat, and it has this list of connections. It's actually reading from /proc, and you can actually understand that if you strace this and grep for proc, these are all the files that netstat reads to understand what's talking to what on your system. Very, very cool stuff. All right, anyways, one of the other things that proc has is all of these numbered directories. And this is a directory per process running on your system. My shell's PID is this. So we can actually look at this directory, just a directory. Let's look inside. Has a lot of stuff about my shell. The fact that it's executable is user bin bash, where the current working directory is, stuff like that, but also its memory map right here. All right, and here is the memory map of my shell. And there's actually also this file, which is a file that is an interface to the actual process memory itself. Let me show you what this means. So bash itself is loaded at this address. I'm going to YOLO this. I don't know if this will work. If we try to read from proc self mem, or not self, proc mem, the bash PID, and we skip to this address, and we try to read 4 bytes, and we do this as root. Cannot skip to specified offset. Bummer. Let's strace it. See what it did. That was going off on a tangent. You can. Oh, wait, no. So it. Where's the skip? Error, cannot skip. Okay, this, DD is trying to be dumb. Let's say, can't show it to you easily here, but you can actually open this file, seek anywhere in memory, and read out memory contents of a process if you want, like a poor man's debugger. All right, anyways, doesn't really matter, but what does matter is this file, and there's also a very nice and helpful thing called proc self. This is a virtual symbolic link. It's actually different for every process, and it just points to its own process ID. So you can do proc self maps, and this cat will open proc self maps. Self will actually be point to cat's process map, proc entry, and maps will be the mappings. All right, awesome. So, so when we do proc self maps, this is cat's map. When we do proc, and then this is a bash variable for bash's process ID. This is bash's mapping. We're going to write a program that will print out its own mapping. It opens it up here. It'll read keep reading. I don't know, whatever, 1,000 bytes at a time, and then writing this out. Actually, let's do this insanity. All right. Let me see if this works, and then I'll explain why it works. Let's include some stuff. It doesn't work. Okay, we open proc self maps, then we read, and then we write a 0. Why do we write 0? Right, 1 mappings, and then whatever read returned. Oh, oops. There we go. Okay. Whew. Amazing. All right. What does this do? This will read hex 1,000 bytes, write whatever it was able to read out to standard output, and then if it'll read hex 1,000 at a time, because if you try to make too big of a read, you don't always have a guarantee that you will actually get that much data, even if there's that much data available. And if it didn't, until it gets less than the data it's trying to read, which for data this small usually means that it's a end of file or something. If on a normal file, it will keep reading. So this basically cats out proc self maps. Awesome. All right. So let's take a look at what this program is like. When we run it, it'll print out its mappings straight from proc, and basically we have a program that's mapped somewhere completely random. It has only its program. It has libc. It has this mysterious page after libc, which was what I think is probably the libc BSS. That is global data that's not initialized and is mapped in a way that is not tracked with this the same file name. Then we have, it's mapped in a way that doesn't map it to the same file, the libc file. Then we have the libld, the dynamic loader in memory as well, with its BSS. Then we have our stack. Then we have a couple of internal Linux mappings, and this is our process's memory space. This is where our process can play around and have its own data. All right, the stack you're familiar with. We've been overriding the stack from level 1 onwards. The program memory you're familiar with from GDB. This is where you put breakpoints, places in here. Specifically, this is the executable memory. This is the text segment of the program, right? And it's this range. In this case, it's only one page, hex 1000 bytes. But in libc's case, it's quite a big range. This goes all the way from 5B800 to 73000. It's quite a big file, right? All right. So let's talk about Malik and Mmap. When we Malik, what happens is that the libc dynamic allocator, which we'll discuss a lot more in baby heap, but which I do expect you to know from the rest of your computer science education, will allocate some memory for the heap and will return a pointer into this memory for you to use in your program. All right? That's Malik, calloc, all of this stuff. What about Mmap, which you'll encounter later on in these challenges, right? If you mmap, let's take a look at what mmap looks like. Mmap allows you to map or unmap files or devices or just plain old memory into the memory space of your process, right? What this means is if you don't want to use malloc and free, you can also use mmap and unmap. It's a higher order thing. You can think of it conceptually as the difference between read and scanf. Scanf is a fancier wrapper around basically read in an analogous way. Malik is kind of a nicer wrapper around mmap. When you mmap memory, you have to do it on a page granularity, which you use 4 kilobytes at a time. So the smallest amount that you can mmap is 4 kilobytes. And if you need, hex 1000 bytes. And if you need 4 kilobytes and 1 byte, then you need to allocate 2 pages, 8 kilobytes of RAM. All right, so we have this mmap call. We give it an address where we want memory to be located. We give it the amount of memory, and then we give it a bunch of other stuff, which I will, which all depends on what you actually want to do with the mmap. But here, we'll just do a simple thing. If you leave the memory as null, it'll pick it'll actually map it. I'll show you what happens. It'll map it at a random location. We give it the address or the size. This has to be a multiple of hex 1000 of the page size. We give it protection access. What's it called? Permissions. So we say, okay, this memory should be readable and writable. And if you actually look deep down inside into what was going on in Baby Shell, how those, if you looked into the source code of those programs, you'll notice Baby Shell was also adding executable. And there are flags, which the Mmap man page describes quite in depth. But basically, all we really need is map anonymous. That says, hey, we're not mapping a file on the hard drive into our memory space. We are actually just getting some memory that we can use. Because the traditionally common and still common use of Mmap is to map files from the hard drive into the memory space of your process, which is super useful when working on large data, for example. All right, and then let's man it again, and then the rest is a file descriptor, which is ignored for anonymous. This is if you wanted to map a file into memory, and an offset into the file, again, ignored. All right, let's see what happens here. Let's print these two pointers. All right, implicit definition of Mmap. To include that, implicit definition of printf. All right, here we go. We received FFFFFF, which means that Mmap failed. That's not an address. That is a -1. And if you look at the return value, on error, the value map failed, which is -1, is returned. Interestingly, 0 is not returned. Mmap does not return null on failure. This leads to a lot of bugs because people tend to check for null, assuming that Mmap will return null on failure. But that's not the case. All right, anyways, let's see what I did wrong. Should I also do map private? You can use Mmap to implement shared memory. Yes, okay, so I made private anonymous mapping. And here is my memory mapping. And you can see that two things happened. One, when I did the Malik, the heap appeared. libc mapped in the heap. You learn exactly about how that happens in the next, or in baby heap. The other thing that happened is that there is, at 7FA7600, right here is my readable, writable, executable region. Got mapped in between the two different mappings of libld. So that's interesting, actually, but we won't go into why necessarily, but this mapping got added. You can see its permissions right here. There's a question on Twitch. If you don't give prot read, right, if you don't give read permissions, will the memory just not be readable? Correct. That's actually a security feature that's sometimes used. There's something called non-readable executable memory to try to prevent code reuse attacks. It's also used to implement pseudo breakpoints in hypervisors, for example. You can set a memory as non-readable, and then you can interrupt the process whenever it tries to read it, do some introspection, and then swap in readable memory for it to continue reading. It's pretty neat stuff. All right, anyways. So memory map basically allows you to get some amount of data, and it has to be page aligned at some address. If I try to, this is 4 kilobytes, if I try to read allocate, if I try to map in 4 kilobytes plus 1 byte, the result is basically rounded up to let's see, where is it now? My readable right, this guy right here. So you can see now instead of from D000 to E000, it's going from D000 to F000. Good stuff. Okay, let's see. The final thing here, I had set this to null. That means choose an address for me. If you notice, it's stuffing it in right where my libraries are. Right, so in terms of address space randomization, there's only 3 random addresses that are actually chosen when the process launches. Is that, well, there's several, but it's not fewer than you expect. One is for the base of your program. The other one is for the location of your heap. The third one is for the location of your stack. And the fourth one is for the location of every other mapping. And then every other mapping is just mapped backwards from that choice. And the reason that we have this mapping in between our other mappings, in between LD and libc, is something got unmapped there. So if you map twice, we'll see that things get allocated we're filling in these holes that got deallocated before. And if we look at the difference between the location of B and the location of C, our two Mmapped regions, it'll always be the same. That's fine, whatever, we'll live with that warning. All right, it's hex 2D00, no matter how many times we run this. The addresses are different, but the offsets between them are the same, which gives us some information. That means if we know where D is, or step B is, we know where C is as well. Right? All right. Okay, hopefully that demystified Malik and Mmap, two concepts that you'll run into in later levels. All right, any questions on that? Otherwise, we'll take a quick look at level 5 someone was asking about. All right, lots of requests. I'll drop a piece of wisdom here about level 7. There's a question of how to guess the last nibble. You very rarely have to guess the last nibble of anything. The last nibble is usually pretty fixed. So if you are interested in, for example, let's print the address of main here, even with ASLR on. You can see that main changes a lot, but the last nibble of main, of the address of main, is always 09. The second to last nibble changes a little bit. Sorry. The last byte is always 09. The the third to last nibble is always 2. And then this the fourth to last nibble is what changes. But of course, that only has 16 possible values. Which means if you are missing only one nibble, and you have all the other information, you can just keep trying until you get that nibble right. Brute forcing is a very, very valid strategy in exploitation. Your exploit doesn't have to work 100% of the time, just needs to work once to get that flag. All right. There we go. All right. Sorry, I was running out of batteries there. Okay, so what else? Let's take a quick look at 5. Actually, let's look at 5.1 because is the
It's all fixed now.
it's all fixed. Awesome. So all the binaries got regenerated.
Just the first two.
Oh, that was just the first 2. All right, so the rest are good. Awesome. Let's take a look at 5. Oh. I thought we were running. We have an hour left?
4 minutes, yeah.
An hour and 4 minutes?
No, 4 minutes total.
Oh, fuck. Oh. All right. Well, we won't be able to solve 5 in 4 minutes. We'll need 5 minutes to solve 5, but we'll take a look. Okay, so challenge has been launched, and this starts getting very helpful for us. Gives us our stack frame. Stack buffer points to 8940, which is RSP plus 0. Base pointer points to C0, RSP plus hex 80. We have 18 8-byte words in our stack frame, including the saved base pointer and the saved return address, for a total of 144 bytes. Input buffer is partway through the stack frame. It's 47 bytes long, but the program will let us overflow it. And in this level, there's no there's no win variable. So what would we do? Of course, as we went through this in class earlier, we will redirect execution to the win function. There's no canaries. The binary is not position independent. And it's awesome stuff. But it lets us send multiple payloads, concatenated together, making sure that the total payload size fits in the allocated buffer on the stack. So, what does this thing do? It does a bunch of arithmetic to keep track, to enforce this calculation, right? So if we try to send it one payload size and say, boom, this is how much we want to write, we fail this assertion. Record size times record number. Record number was 1, record size is 1, 2, 3, 4, is less than the size of the input. We failed this because 1, 2, 3, 4 times 1 is not less than 144. Let's take a look in IDA. Okay, that was stupid. Let's just do. Let's take a look at IDA. And see what happens here. All right, we have our assert. This is what we were failing. We passed this assert that the record size has to be greater than 0. We passed, otherwise, if if the record size was 0, well, likely we'd read in 0 bytes for every record, but also this would return 0 and probably pass in a bad way. All right, so it makes sense. But then this seems like a pretty legitimate block, right? And let's take a look at how this is implemented. We take whatever this variable is. This is presumably so this is the record size. No, this is size of each payload. Yeah, so this is record size. And this is the number of payloads, payload num. And the result, record size, payload num, IMUL'd together compared against 7. Why compared against 7? I guess kind of, why would this be comparing against 7?
Is that what the buffer size is supposed to be?
I guess it must be. No, it says the input buffer is 47 bytes long. 7. Okay. This doesn't affect solvability, but it's an interesting hurdle. But basically, it compares this. If it's too long, it'll just assert out. So, remember the lecture on integer errors that lead to memory errors, right? There is a type of corruption where you do a calculation, and because you're not computing on a brilliant, infallible human mind, you're doing calculations on a feeble machine with machine limitations. One of these limitations is this. When this multiplication happens, there's a maximum number of bits that can hold the result. What happens if the result is bigger than that number of bits? Or what happens? Well, answer that question first. What happens if that result is bigger than a number that can be expressed by the number of bits that are that are available in the register that the result gets into. And on Twitch, someone said Int Overflow. So think about an integer overflow. Think about how can that be induced here to pass this check. That actually is a very common, I wouldn't say very common, but it's a very real bug that affects programs to this day. We have research projects in my research lab right now where we're analyzing thousands of programs for integer-based flaws like this and finding hundreds of them, which is pretty exciting. And now you are exploiting that with this level. All right. We're going to leave it at that for today. We'll have office hours tomorrow. And otherwise, keep hacking. You as well. Good luck. All right. Ciao.